Hello students, this video is for a quick review of week 3. So here's a quick refresher on how the triangle applies to the forces that we are drafting and their components that are either vertical, such as Fy, or horizontal, such as Fx. And here's a quick refresher on how to apply SOHCAHTOA when you're trying to solve for different sides of the triangles. This last week, we covered the vector analytical addition. Here we saw how to use force components of multiple forces to find their resultant for the y components and for the x components. In some problems, it is necessary to develop or set up equations for a system of linear equation explanation. For when you have two unknowns, develop an equation and substitute your variables in another to replace and eliminate one unknown. You can click at the bottom of your PDF file for the link. So now that we see the accumulated forces and how they correspond to the resultant, we can use the Pythagorean theorem and we can say that the force resultant is equal to the square root of the force resultant x component squared plus the F resultant's y component squared. Last week, you also took quiz number 2. Here's a quick review for it. Looking at the vector component sign, you have to fill in the blank. The x component is the horizontal component of a vector. If a vector's x component points to the right, it is positive. If a vector's x component points to the left, it is negative. The y component is the vertical component of a vector. If a vector's y component points up, it is positive. And if a vector's y component points down, it is negative. Now let's take a look at assignment number 2. For this problem, we had to show analytical solutions using force components, and then we had to check them graphically. To start off, looking at 2.9, 3 members of a truss frame into a steel gusset plate is shown. All forces are concurrent at point 0. Determine the resultant of the 3 forces that must be carried by the gusset plate. To begin, we must first draft the problem in AutoCAD. This is to get the direction of our forces and to also get any magnitudes that we are given. Second, we need to find the x components of all the forces, or draft them in AutoCAD to quickly find their value. Looking at F2, our force of 12K, which points to the left, is a negative 12K force. And you can see there's no translation in the y direction, so our F2y will be 0. Next, let's take a look at F1. F1 is equal to 10K. By using AutoCAD, we can dimension and find that F1x is equal to 5K, or we can use the equation Fx1 is equal to F1 times the cosine of theta, or Fx1 is equal to 10 times the cosine of 60. Also find with a dimension that F1y is equal to 8.66K, or it can also be found with Fy1 is equal to F1 times the sine of theta, which is equal to 10 times sine of 60. Now let's take a look at F3, which is equal to 18K. F of x is equal to 12.73K. This can be found by f of x3 is equal to f of 3 times the cosine of theta, which is equal to 18 times the cosine of 45. And here we can also find f of y is equal to 12.73. Do notice that because we have a 45-degree angle, both our f of x and f of y are equal to each other. Our f of y is negative, though, because of its direction, and f of x is positive because of its direction. Now we put it all together. Let's take a look at the resultants, our x components. We can see that if we sum up all the forces x components, that's F1 plus F2 plus F3, we can say that the sum of the resultant x components is equal to the F1 x component, F2 x component, F3 x component. And we can solve for our x and find that it is equal to 5.73k. And the same applies to the Ry components. We can sum up all the Fy force components and find that the sum of the resultant y components are equal to negative 4.07. And the next thing to do is to graph our resultant by using the Rx is equal to 5.73 and Ry is equal to negative 4.07. Fourth, we find the resultant's magnitude using the sum of our x components and the sum of our y components. We can also use the Pythagorean theorem, c squared is equal to a squared plus b squared, or in relation to our resultant, r squared is equal to rx squared plus ry squared. We plug in the numbers that we found and find that the resultant has a magnitude of 7.3k. And you can see that here within the aligned dimension. Next, we find the resultant's direction. We can do this by using, again, the sum of Rx components and the sum of Ry components, and the function tangent of theta for the resultant is equal to Ry divided by Rx, and theta of the resultant is equal to the tangent inverse of 4.07 divided by 5.73, and we find that the resultant's theta is equal to 35.38k. And the final thing for this problem is to do a graphical check. We can see here by creating a tip-to-tail graph of all the forces and the resultant as well. You can see here that by stacking up the forces consecutively, starting with F1, then F2, and finally F3, and the resultant checks out. Now let's take a look at problem 2.11. This one reads, a laborer is hoisting a weight W, which is equal to 200 pounds, by pulling on a rope as shown. Determine the force F required to hold the weight in the position shown if the resultant of F and W acts along the X of the boom. For this problem, we have two unknowns, R and F. Solving it graphically is very easy with the tip-to-tail graph, like we did in assignment number 1. In order to solve it analytically, it is necessary to develop a set of equations. A system of linear equations is used when you have two unknowns. Develop an equation and substitute your variables in another to replace and eliminate one unknown. To start off, let's look at W equals 200 pounds. This force is only a vertical, meaning there is no x component. So our Wx will equal to 0. Our Wy will actually be equal to negative 200 pounds. Now let's take a look at force F, which is unknown. Because we do not know the value of the x and the y components of forces for F and R, these are our two variables. Let's begin with the direction. Our problem gives us two directions from the vertical axis. We can find out the correct theta we will work with by subtracting 30 and 20 from the right angle created by the axes. Our theta for this force will be 20 degrees. Let's begin by looking at Fy. Fy can be found by using the function Fy equals F times the sine of theta, or F times the sine of 20 degrees. Because we do not know the value of Fy or F, we leave this portion as a function. F of y is equal to negative 0.3420 F. Don't forget the negative. Let's take a look at the f of x component. We can find this by using the function f of x is equal to f times the cosine of theta, or f times the cosine of 20 degrees, and that is equal to f of x is equal to negative 0.9397 f. Again, don't forget the negative. Let's move on to looking at force R. To begin, the theta we will be working with will be 90 minus 30, which is 60 degrees. We can find Rx by using the function Rx is equal to R times the cosine of theta, or R times the cosine of 20 degrees. We find that Rx is equal to 0.5 R. We'll leave this portion as a function. Now let's look at finding the y component for force R. Let's move on to look at the resultant's y component. To begin, let's start with using function ry is equal to r times the sine of theta, or r times the sine of 60 degrees. We find that ry is equal to 0.866 r. Alright, so now that we have all the functions, let's go ahead and put this all together. We will begin with the resultants Rx components, f of x and wx. And we will sum these up to find the resultant x components. We already have the equation set up for plugging in to our function. The sum of resultant x components is equal to the negative fx plus wx. We plug in the numbers and we find that the resultant is equal to negative 1.88f. We have gotten to a point where we can no longer solve for these variables, right? So we're going to leave these as they are for now, and then we're going to move on and plug them in later. For now, let's go ahead and look at the resultants, our y components. We have f of y and wy. We will sum these up to find the resultant y component. And the sum of the resultant's y components is equal to negative fy plus negative wy. We plug in all the numbers and we find that 0.866 times r is equal to negative 0.3420 f plus negative 200 pounds. We use the equation that we developed earlier and we substitute here for r, and then we solve for f. We find here that f is equal to negative 155.039. Now we use this portion of the equation to plug back in and solve for r. And we find that the resultant is equal to negative 291.47. Let's take a look at the graphical check. We will create a tip-to-tail graph starting with W is equal to 200 pounds in a downward direction. We will then stack on the direction for F. The distance is unknown, so for now, the direction will work for us. Next, we know that the resultant will end wherever the force W began. So again, we do not know the distance, but we do know the direction. So we stack it on. The last thing to do is to use the fillet command and fillet the lines. Here we see, once we've filleted the lines, that R is equal to 292.3804 and F is equal to 155.5724. It very closely matches the answers we got. This is because we are constantly rounding up or down to the nearest either 2 decimals or 3 decimals or 4 decimals. Alright, now let's look at problem 2.12. This one reads, one end of a timber roof is supported on a brick wall, but not securely fastened. The reaction of the brick wall can therefore be only vertical. Assuming that the maximum capacity of either the inclined or horizontal member is 7 kN, determine the maximum magnitudes of F1 and F2 so that their resultant is vertical through the brick wall. Here we have the inclined member and the horizontal member. In this problem, we're being asked to pretty much compare two scenarios. Okay, the first one we will check. We will set the horizontal member to have a capacity of 7.0. In the second scenario, we will set the inclined member to have a capacity of 7.0. We can either graph this out using tip-to-tail method, like I show here, or you can go ahead and use the functions to solve for either the inclined member. Here we found that F is equal to 7.2 kN. And in this case, we solved for the horizontal member. And we found that f of x is equal to 6.34. Looking at the values we found, we see that in our first scenario, where our horizontal member had a force of 7 kN, our inclined member had a force of 7.72. This here will not work because it is now over capacity. In scenario number 2, we set the inclined member to have a force of 7 kN. We found that our horizontal force would then be 6.34 kN. This here would work perfectly because our inclined member would be under capacity. This brings me to the end of today's review. Before we take off, though, I do want to remind you that for this course, we will be using an assignment template in AutoCAD. Please refer to the AutoCAD files for assignment template located under 2344 Statics and Strengths of Materials Week 1 content folder on EPCC's Blackboard. Use the appropriate unit in AutoCAD files as a starting point for your assignments. Set up units per the AutoCAD file depending on what the problem requires. The template has only a few scale preset settings for viewports, text styles, dimension styles. If you need help with AutoCAD settings for viewports, text styles, dimension styles, or anything else, please email me so I can walk you through any questions you may have. Fill in the assignment template with the appropriate information. Upon completion of the assignment, print your work in PDF format and submit your work through Blackboard. Also, in regards to the assignment template in AutoCAD, there is a how-to video that is now available in the course content Week 4 folders. You can click here for the link of the video as well.